The purpose of this video is to give you a basic introduction to how Complexit uses artificial intelligence in its suite of techniques to conduct a case-based analysis of social complexity. As you look down the left here, you'll see that AI, artificial intelligence, is the third tab in the suite of analytic procedures available in Complexit. When people say this word, artificial intelligence or artificial neural nets, it sounds a bit, overwhelming, but it isn't actually. And if we break things down, it actually makes a lot of intuitive sense, particularly the approach we take. You'll see that here, the SOM, the self-organizing map, which was invented by Kohonen, a Finnish computer scientist, absolutely brilliant. When Kohonen invented this, he meant it as the following. It's a type of artificial neural net trained using unsupervised learning to produce a low-dimensional map, and is therefore a type of dimensionality reduction. So you say to yourself, well, what exactly does that mean? It really means this. Like cluster analysis, the data will be clustered. The SOM map is a representation of the SOM attempting to fit the data to identify the best clustering of the data. Here is a very simple example of two clusters. This is voting behavior amongst U.S. Congress people. On the left is voting more conservative, on the right is voting more liberal. And you can see that when we look at the variables that go to explain this inevitable clustering, you're taking a lot of complexity. This is an n-dimensional space. This would be all the particular variables, right, that you have, for example, in your cluster analysis. Remember, in the case of our study, we're looking at the Welsh Multiple Deprivation Index. So here are all the factors, right? How do you take all these factors and condense them in a way to create a visual map of them? Well, cluster analysis can't do that. We can see how the cases themselves fit with the clusters, but we really don't understand how all the factors associated go together. And that's what's strong about the SOM, is that it is a visualization of highly complex data, which it reproduces visually in a two-dimensional or three-dimensional space, compressing all that complexity into something that can make sense. And here's the interesting thing. Since the 80s and 90s, when neural nets and artificial intelligence really took off, up to today and the more recent developments in deep learning, the continued critique is that neural nets are a black box. And my constant frustration, and colleagues of mine working with self-organizing maps, of which Kohonen is the first, but also one of many, is that, well, if you use this technique, you actually can get inside the black box because the neural net tells you exactly visually what it did. Here's the cluster solution it arrived at, and here's how the factors associated with that cluster solution went into play to determine those. So you see over here, a group of highly conservative voters. They're part of the Republican Party. They view bankruptcy and abuse as highly important. Border protection is highly important, right? And U.S. patriotism and so forth, right? That fits with conservative versus, say, liberal. You see over here, in terms of border protection not being as serious an issue, private property rights not being as serious an issue. However, stem cell research being very important, school readiness, right? So all the sort of things you think of as sort of typically liberal. And that should make visual sense and also intuitive sense, and that's what the data shows. So that is what the self-organizing map is it's a form of unsupervised learning that does that. Now here's the key with the unsupervised learning and why this is in Complexit. You're building and importing your data, right, from a case-based perspective. You're clustering your cases, but here's the key. We start with the k-means, which again, the other videos deal with. You can go watch the video on how to build the database and how to cluster your cases. We start with k-means because it requires you as the user to have an idea of what number of clusters you're actually looking for. It doesn't have to be perfect, and it requires you to sit in there and run several analyses till you get a solution that you think is reasonable. The reason we do that first is we want human expertise in front. Then we turn to the SOM because it is, as this says, an unsupervised form of learning. What that means is the SOM is going to arrive at its own cluster solution, and then we will take that cluster solution and compare it to your cluster solution when we get to the last step in confirming and exploring the model by visualizing your solution and the SOM solution and doing an analysis of those two different approaches. So this is what makes the SOM very useful when it comes to doing the types of analyses that we're doing, and why Kohonen's work is so incredible. And to just further point this out, want to make two additional key things here. First of all, if you look at Scholarpedia and look at Kohonen and Honkla's definition, it is clear as to what Kohonen meant. A computational method for the visualization and analysis of high-dimensional data. Right? It's a very simple definition. Visualizing high-dimensional data in a way that can be intuitively made sense. So exactly the problem that exists with neural nets is exactly not a problem with the SOM. Again, now, you've seen how this plays out, and we've taken a look at it. But what we haven't done is kind of gotten a feel for how that actually takes place. On YouTube are some cool videos. Here, for example, you can see how this SOM goes about fitting. So here's the map, basically, the dimensional space in which the data is situated. In this case, it's showing you on 2 dimensions, typical of the principal components, but don't worry about that. What's key here, though, is to watch how, as the algorithm is run over and over and over again, it gets closer to a solution, and it begins to look like the net it is. Netting that solution across time until it gets more refined and better at the fit. Until finally you get to the end and you've got a reasonably good fit of the data. Now, there's a variety of software packages out there that you can use. The one that we originally used back in the 90s and early 2000s was developed by Kohonen. You actually ran it in MATLAB. It has a very high, what I would call a nerd factor on it, meaning you really got to know how to do programming and you have to have a high level of expertise in MATLAB and so forth. Our goal with Complexit, obviously, was to make this process much simpler so that one could move from importing data to clustering to then simply running the SOM and doing that. So we turned to the RStudio software and went in search of people that would be doing the type of work we're doing. And Natalie Vieleneks and her team have done some fantastic work in this area, and we borrowed from their work. You can see their particular approach is called Sombrero for the SOM, and it is basically using Kohonen's particular algorithmic approach. On the CRAN site for R, you can actually find all the information, technical information you want for those who are more interested in a more in-depth analysis, including a PDF that walks you through basically how Sombrero does its work. For us, the key here is that we're attempting to create an unsupervised approach to the analysis of your data in order to take that unsupervised approach and compare it to the one you did. So the actual running of the SOM is quite simple, and we've purposely created it that way. In addition to the tutorial you're watching here, you can go, as I clicked, to the CRAN site for Sombrero to read what their work has been doing on this. And then also there's a nice basic introduction to the self-organizing map. You can click here. But for those basically coming and use this, we've set the parameters up as a nice default set, which the majority of the time you would have no need to mess with. So just run it as it is, and it's nothing more than, at this point, clicking the button. The key here, though, is you want to look at what's called topographical error and quant error. The goal is to get these as close to zero as possible. They're unstandardized representations of the error, so you can run your analysis several times. See 7.18, 7.53, 7.10, and your topographical error staying at 0, which is a pretty good fit. And so again, just like the cluster analysis, you're trying different solutions to get a feel for which looks to be the best solution for the data. And generally speaking, it seems they're all sort of sitting in about the same range of error. Here we've gotten the lowest quant error possible and a reasonably low topographical error. For more in-depth analysis, we will have a video that will specifically talk about how to read these output statistics. But for now, it's sufficient to just work with the defaults as they are and then to move forward. The key here, though, is to show you then the SOM map that's produced in Complexit. We're actually going to have a video talking about how to run this whole thing, but what I want to show you here is this key thing. Is each quadrant here, 1 through 5, 6 through 10, all the way over to 21 through 25. These 25 quadrants each represent a cluster. And you're able to actually produce on this map the k-means cluster solution that your data was initially identified with, and then the actual case, and then the cluster that the SOM put it in. Obviously, the goal would be to see that the solution you arrived at has similarity to the solution that the SOM arrived at. But here's the key. In your cluster solution, you can control the size of your grid. So if you run this, all right, now you see this does push the quant error up a bit, so it's not necessarily getting as good a fit. But when you go to compare and visualize your results, you'll see it has shrunk down because now you're dealing with 9 clusters rather than the larger number. So you can work with that. So for example, if you wanted to refine that even more, you can do so to get a reasonably good fit. But the key is that it will distribute your original k-means cluster solution in a more diverse manner. So it's not a one-to-one fit per se between the solution provided by the SOM and the k-means, as much as it is an art and science of exploring this back and forth relationship between the SOM solution and the cluster analysis solution. And there is, for those who are interested, a reasonably nice literature on the relationship between cluster analysis using k-means versus the clustering solutions that are produced in the neural net self-organizing map. So with that, you have a basic sense of how this approach works.